This week we're looking at sequences. To get warmed up, pause the video and have a go at these questions. Okay, so in the first sequence, hopefully you spotted all we're doing to get from one term to the next is adding 3. So the rule that we used was adding 3, and the next term in that sequence would be 17 add 3, which would be 20. For the second sequence, again, the same thing was happening each time. We were just dividing by 2, so the rule was dividing each term by 2 to get the next term, so 1.5 divided by 2 would be 3/4, or 0.75. The next sequence is what's called a Fibonacci sequence. This one's a little bit more difficult. You add up 2 terms to get the next term, so 1 add 1 is 2, 1 add 2 is 3, 2 add 3 is 5, 3 add 5 is 8, and 5 add 8 will give us the next term, which will be 13. And this last sequence here, a lot of people find this really difficult, but once you spot it, it's really straightforward. This is just the numbers 1, 2, 3, 4. We're taking the first letter of each number. 5, 6, so the next number is 7, which will give us S. There are lots of types of sequences, but this week we'll be focusing on 3 types: geometric, arithmetic and quadratic. These 3 terms will be explained as we go along. In particular, you'll need to find an nth term formula for arithmetic and quadratic, and we'll be using surds in some of the geometric and arithmetic sequences. Using surds and quadratic sequences are both higher level content. Pause the video and have a look at the first 3 questions. Hopefully you noticed then that the main difference was that in the first sequence we were adding on an amount each time, in this case adding 2, whereas in the second sequence we were multiplying by the same thing each time, in this case multiplying by 5. What's the same about them is that there is a rule that we could use to continue the sequence. Which one will get greater than 100 first? Well, 75 times 5, that will be greater than 100, whereas 7 plus 2, we're only going to be at 9. So sequence B will be greater than 100 first. Sequence A is an example of an arithmetic sequence, a sequence where you add on or subtract the same amount each time. Sequence B is a geometric sequence. That's when you multiply by the same thing each time. You could be multiplying by a fraction, which is a bit like dividing. For example, if you multiply by a half, it has the same effect as dividing by 2. Pause the video and have a go at the last 2 questions. So, first 4 terms of 2 more geometric sequences, one ascending and one descending. So an ascending sequence, we could have a sequence that starts with 3, and then if we multiply by 2 each time, 3 multiplied by 2 would be 6, multiplied by 2 would be 12, multiplied by 2 would be 24. So that would be the first 4 terms, and that is ascending, terms getting bigger as we go along. A decreasing one, where we start with a value and we're going to keep multiplying by a fraction to make the terms get smaller. So, for example, we could have 24 and then times it by a half, that would give us 12, times it by a half, that would give us 6, times it by a half, that would give us 3. It just so happens I've done the same sequence in both cases there. The common ratio for this first sequence, the number that we're multiplying by each time, would be 2, and the common ratio for this second sequence, the number that we're multiplying by each time, would be a half. Pause the video and have a go at this question. This is what we call an exponential sequence, one where we are multiplying by the same thing each time. It's a geometric sequence. So if we start with £1 in January, £2 in February, £4 in March, and keep doubling, that's £8 in April, and so on, well, exponential sequences get very big very quickly. You'll have heard on the news about how the coronavirus has grown exponentially, which is a real life example. So, would it be realistic for a whole year? Well, let's see, January, February, March, April, May, June, all the way to December. So we've got 1, 2, 4, 8, and so on. If you keep the pattern going, what you'll see is by the time you get to December, we're going to have rather a lot of money, £2,048. If Teddy's got that, by all means he could keep saving it, but for most people that wouldn't be realistic. This should be revision. Pause the video and have a go. So in all cases for these sequences, it seems that we are adding 5 each time to get from one term to the next. So these, although they're negative numbers, minus 20 add 5 is 15, minus 15 add 5 is minus 10, and so on. And here with these decimals, same thing again, 13.2 add 5 is 18.2, and so on. Now there's lots of ways to get to the term that goes on the end of the sequence. A lot of people find it easiest to look at the 0th term. If we say that n is 1 for the first term, 2 for the second, 3 for the third, 4 for the fourth, and so on, if we went back to the 0th term, so do the opposite of plus 5 and subtract 5, well, what would we get there? 2 minus 5 would be minus 3. And that does give us the nth term formula for this sequence. 5n minus 3, if n is 1, 5 times 1 is 5, take away 3 is 2. 5 times 2 is 10, take away 3 is 7. You can see how that's working. Same sort of idea for this one then. If we were to go back to the 0th term, we would have minus 25. So this sequence will be 5n minus 25. And finally this sequence, if we were to go back to the previous term, that would be 8.2. So it's going to be 5n plus 8.2. Have a go at these. Pause the video. So we've got the first sequence where in each case we are adding 4. So we know the formula starts with 4n, and then if we go back to the 0th term, so if we subtract 4, 3 minus 4 will be minus 1. Same sort of idea here. This time we're subtracting 2 each time, so it will be minus 2n, and then if we go back a term, so do the opposite of minus 2, this time add 2, the 0th term would be 22. In this case, for each term we are adding on 0.7, so if we go back to the 0th term by subtracting 0.7, that will give us minus 0.1, 0.6 minus 0.7 is minus 0.1, and 0.7n because we're adding on 0.7 each time. And finally, for this one here, in each case we are subtracting 0.3, so that will be minus 0.3n. And then if we do the opposite to go back, we would have 5.9 plus 0.3 would be 6.2, so that would be 0.3n plus 6.2. The video and have a think about these questions. So, is it impossible for a geometric sequence to alternate between positive and negative numbers? Well, actually, no, it's not impossible. If we said that the common ratio was, say, minus 2, we could start with 1 times minus 2 would be minus 2, times minus 2 would be positive 4, times minus 2, times minus 2, times minus 2, and so on. We're alternating between positive and negative numbers. An arithmetic sequence has to be ascending or descending. It can't alternate between the two. Now that one is true, because if you think about it, if you are adding the same thing each time, let's say you're adding 2 each time, we'd have 1, 3, 5, 7, that's going to keep going up and up forever. If you were subtracting the same thing each time, let's say if we were subtracting 2, we'd have 10, 8, 6, 4, that's going to keep going smaller and smaller forever. So it can't alternate between the two. That is a true statement. And finally, if you start with a positive number and the common ratio is a half, you will eventually reach 0. Well, not really, but we will get very close to 0. No matter what number you start with, it could be a really big number. Fairly quickly, you get into fractions. I'm just going to start with 1. With a ratio of a half, we'd have 1, then a half, times another half is a quarter, times another half is an eighth, times another half is a 16th, and so on. You can see that these fractions are getting smaller and smaller and smaller, but it will always be 1 over something, so we'll never actually reach 0. The same would be true no matter what number we started at. We would keep getting smaller and smaller and smaller, but we won't actually reach 0. Here we've got a sequence involving surds. It's geometric, so we're going to multiply by the same thing each time, and in this case the common ratio, the thing we're multiplying by, is √2. Pause the video and have a go. So the first term was 6. The second term is going to be 6 times √2, which is 6 √2. Now the next term we're going to have to times by √2 again. So that's 6 times √2 times √2. Well, √2 times √2 is just 2, and 6 times 2 is 12. We're going to then multiply by √2, so we have 12 √2, and multiply by √2 again. Well, √2 times √2 is 2, times 12 is 24. And there we've got the first 5 terms in their simplest form. If there were an even number of terms, and let's just put one more term in so we could see what we'd have if we had an even number of terms, so that would be 24 √2. Well, every other term has got a √2 in it, and every other term is an integer. So half of the terms will be integers and half of the terms will involve surds. Okay, so this one's a bit harder, but still you have to think about what do we add on each time, because it does say it's an arithmetic sequence. Pause the video and have a go. So √8, well, √8 is, if you remember from before, if we look for square numbers that go into 8, that's going to be √4 times √2. 4 is a square number, so square root of 4 is 2, so √8 is 2 √2. So we could say we've got 2 √2 plus 1 for a term, and then the next term is 3 √2 plus 4. So if we look at the surds, if we had 2 √2 and we've gone up to 3 √2, we must have added on √2. And if we look at the integers, if we had 1 and we've gone up to 4, we've added 3. So it looks like our common difference is √2 plus 3. So if we go back, we need to know what number would we have to add on √2 plus 3 by to get to √2 plus 1. Well, if we had 1 √2 and we added √2, we'd get 2 √2. And if we go back 3, we'd be at -2, because -2 add 3 would give us 1. So the first term of the sequence is √2 minus 2. Here's a challenge. Have a go at these sequences. Pause the video. So in this first sequence, we can see that each term has an integer 3 at the start, and then in the first one we don't have any √5s added on. Then we've got 1 lot of √5, 2 lots of √5, 3 lots of √5, so it would seem to be 4 lots of √5 should make the next term. So the common difference, the amount that we've added on each time, has just been root 5. In this sequence, we are alternating between surds and integers, which we saw before in the geometric sequences. So it looks like we should be multiplying by the same thing each time. So whereas the first sequence was arithmetic, this one looks like being geometric. So to get from 2 to 2 root 2, we've multiplied by root 2. Let's just check. If we were to multiply by root 2 again, the root 2 times root 2 would make 2, times this 2 would make 4. So it does seem like we're multiplying by root 2 each time. So our next term, if we've got 8, the next term would be 8 root 2. In this sequence again, we're alternating between surds and integers. So we're looking like having a geometric sequence again. So 2 root 3 to make 12, well, let's try root 3 and see if that works. Root 3 times root 3 would be 3, so 2 times 3 would be 6, but we don't want 6, we want 12. So maybe if we times it by 2 root 3, that would double it up to give us the 12. Let's try that for the next term. Multiplied by 2 root 3. So 12 times 2 would be 24, times the root 3 would be 24 root 3. And if we just try one more, just to really convince ourselves, root 3 times root 3 is 3. So we've got 24 times 2, which is 48, times 3, 144. So it looks like we need to multiply by 2 root 3 again. So 2 root 3 is our common ratio. And 144 times 2 would be 288 times root 3. And finally, this next term, this next sequence rather, we have got lots of terms and all the terms have got some surds in, suggesting that's arithmetic. So 5 plus root 7, 1 minus 3 root 7 minus 3. Well, let's split it up. Let's look at just these numbers here first. So 5 minus 4 would give us 1, and then minus 4 would give us minus 3, minus 4 would give us minus 7. So it looks like we are taking away 4 each time. And let's look at the surds. We've got root 7, and then minus 3 root 7s, minus 7 root 7s. It looks as if we are taking away 4 lots of root 7 each time. So our last one, we're at minus 7. If we subtract 4, that would take us to minus 11. And then if we have minus 11 root 7, we take away another 4 root 7s, that will take us to minus 15 root 7. These are called quadratic sequences because they're related to square numbers. So if we start with n squared, 1 squared, 2 squared, 3 squared, 4 squared, the first difference is the number that we're adding on each time. So in this case, the first difference was 3, 5, 7. Then the second difference is if you have a look and see what you're adding on between these numbers. And in this case, we've had 2. So the second difference was 2, and the nth term for this, well, this is just n squared, 1 squared, 2 squared, and so on. For this one, it's 2 lots of n squared because it's just the n squared numbers times 2. But what would be the second difference? Have a go. So you should have found, if you looked at 2, 8, 18, 32, 2 add 6 is 8, and then 8 add 10 is 18, and then 18 add 14 is 32. The second difference, or 6 add 4 is 10, and 10 add 4 is 14. So the second difference in this case was 4. If you repeat the process, you will have found that you got 6 for the second difference when it was 3n squared, and 8 for the second difference for 4n squared. Hopefully you realised that if you half the second difference, you get the number of n squared. We can use this to work out the nth term formula for a quadratic sequence that's not just a multiple of n squared. So this sequence here, 1, 10, 23, 40, there's nothing that we can just add on each time, because, for example, if we add 9 here, but then from 10 to 23, that's adding 13, and from 23 to 40, that's adding on 17. But if we look at the second difference, 9 add 4 is 13, and 13 add 4 is 17. So the second difference is 4, which means half of that is 2, so we're going to start with 2n squared. So half of the second difference gives us the number of n squared. Now the sequence 2n squared is just 2 times the square numbers, so if you remember that the n values would just be 1, 2, 3, 4. So 2n squared, well 1 squared is 1 times 2 is 2, 2 squared is 4 times 2 is 8, 3 squared is 9 times 2 is 18, 4 squared is 16 times 2 is 32. Remember BIDMAS, we do the squaring before we times by 2. Now, the actual sequence that we want has got 1, 10, 23, 40, and we know it's going to start with 2n squared, but what we're missing is what we need to do to 2n squared to get to these values. Well, what we can do is see what we would literally do to get from 2 to 1. We'd have to subtract 1. To get from 8 to 10, we'd have to add 2. To get from 18 to 23, we would have to add on 5. And to get from 32 to 40, we would have to add on 8. Now, what's going on here? This is just an arithmetic sequence. We're adding on 3 each time. You can see that they filled in the 3n for us there. So, what goes here? If we work back, what would be the 0th term? If you're at -1, if you take away 3, the 0th term would be -4. So the final answer is that the nth term formula, 2n squared plus 3n minus 4. I missed out filling in this bit here. So the second difference was 4. So the coefficient of n squared was half of 4, which was 2. That's where the 2n squared came from. So the 20th term is 856. That should mean if we did 2 times n squared, so 2 times 20 squared, plus 3 times 20, and then minus 4. Well, 2 times 20 squared, well 2 squared is 4, times 10 times 10 will give us 400, times 2, that's 800, or you could use a calculator. 3 times 20 is 60, and take away 4, so that's 860, take away 4, which is 856. Pause the video and have a go at these questions. Let's look at the first one. We start with 2, 9, 22, 41. So first of all, look at the differences. Between 2 and 9, we'd add on 7. From 9 to 22, we'd add on 13. And from 22 to 41, we would add on 19. So from 7 to 13, we add on 6. From 13 to 19, we add on 6. So the second difference is 6, and half of 6 is 3. So we know it's going to start with 3n squared. So we have got 3n squared. Well, let's look at n first, that's easier. So we've got 1, 2, 3, 4. 3n squared. 1 squared is 1 times 3 is 3. 2 squared is 4 times 3 is 12. 3 squared is 9 times 3 is 27. And 4 squared is 16 times 3 is 48. So there's 3n squared. And what we need to do is work out what do we need to do to get from 3n squared to the numbers we actually wanted, 2, 9, 22, 41. Let's have a look. So from 3 to 2, we take away 1. From 12 to 9, we take away 3. From 27 to 22, we take away 5. And from 48 to 41, we take away 7. So the formula for this, we're going from -1 to -3, that's subtracting 2, subtracting 2, subtracting 2. So we've got -2n, and then if we go in the other direction to get the 0th term, -1 plus 2 would be 1. So -2n plus 1. So our final answer is made up of 3n squared minus 2n plus 1. There's quite a few steps in doing these. An example, if you look at the differences between the values, we get 14 and 26 and 38. So the second differences are 12 each time, and half of 12 is 6. So that tells us our formula is going to start with 6n squared. So again, if we start with n, is 1, 2, 3, 4, 6n squared will be 6 times 1, which is 6, 6 times 4 is 24, 6 times 9 is 54, and 6 times 16, or 6 times a 60, so that goes 96. Then we need to see what's happening to make the numbers in the sequence that we actually ended up with. So the final sequence is going to be 2, 16, 42, 80. Let's have a look here then. To get from 6 to 2, we'd have to take away 4. From 24 to 16, we'd take away 8. From 54 to 42, we would take away 12. And from 96 to 80, we would take away 16. So, term to term here, looks like we are subtracting 4 each time. So let's go for the 0th term. We add 4, and minus 4 plus 4 will be 0. So we're going to get a minus 4n plus 0. We don't really need to write plus 0. So the final answer will be 6n squared minus 4n. That's the nth term for this sequence here. And the final answers for the last two, for the sequence 1, 8, 21, 40, it was 3n squared minus 2n, and for the sequence 4, 18, 44, 82, you end up with 6n squared minus 4n plus 2.